So there's a few things that can happen at critical points of multivariable functions, and we'll talk about what it means to be a critical point in a little bit. In this chapter, we're going to assume that we have only nice functions that don't have like weird sharp edges or corners or anything like that. We didn't really deal with that in 2 dimensions either, but here we're definitely not going to worry about that kind of thing. So all of our functions will be nice, smooth types of things. So at a critical point, we can have things like something like this. So this is like a cup, where at the very bottom of this, we have a minimum. So if we were to look at this just from one side, we could see like a parabola, and we would definitely see a minimum. So we're really just sort of making that parabola 3-dimensional. And it doesn't necessarily need to be a parabola, but here we have sort of this like cup shape, which would be a minimum. We could have a maximum also. So if we just like flip that over, now we have like a mountain, which would be a peak. So that would be a maximum up there. You're not going to have to draw these graphs to see them. So we could have a minimum, which is going to be sort of this like cup type of shape or a valley. We can have a maximum, which is like a peak, like a mountain. There's one more thing that can happen here. And this I'm going to see if I can draw. Okay. So if we have a minimum in one direction, so this would be like a parabola type thing. But now we have 3 dimensions. So if we look at this in another direction, maybe we would have a maximum in that direction. And now this surface, this would all be filled in. If we look at it from one dimension, it's a valley, like a minimum, but if we look at it from another angle, now it's a peak. And this here, which we will see a better picture of in a moment, is a saddle point. So if you imagine like a saddle that you would ride on in a horse, if the direction that you're facing, it's sort of scooping upward. So you have a little lip up in front of you and behind you. But over on the 2 sides where your legs are going, there it's curving downward, like over the horse and under your legs. So that's what we're looking at here. Another time when we use this word saddle is if you're climbing up Mount Humphreys, there's a ways you go up, and then at some point you reach the saddle, which is where if you kept going the same direction, you would go up and over. But if you turn, now you're going up one peak or the other peak. So this is a thing that does not happen when we're working with just 2 variables, just x and y, but it does happen once we add that 3rd dimension. So all of these are happening at critical numbers. And these are the pictures in the book. So we have, they did the opposite order, but our maximum, which is like a cone, our minimum, which is like a cup, and then the saddle point. So critical points So remember, we're working in X, Y, Z now. So I'll give you a moment with that definition. So thinking back to when we were maximizing in chapter 4, critical numbers were where the derivative equals 0. Or is undefined, we're not going to worry about that in this chapter. So we have that same concept of what a critical point is here. It's going to be a point because we have an X and a Y coordinate here. We have that same concept of the derivative being 0, but since we're working in multi-dimensions, the partial derivative has to be 0 for all of the variables. So AB, this XY point, is a critical point if the partial derivative with respect to X is 0 at that point, and the partial derivative with respect to Y is also 0 at that point. So it's not enough for one of them to be 0, they both have to be 0 for it to be a critical point. The process for finding these maximum and minimum has a few steps. There is a theorem in the book on page 444, but I have kind of summarized it. So I'm going to go to the next page. We're going to go through all of these steps and I have them written down. Oh wait, maybe I don't have them written down. Okay, I'm going to copy and paste them below for our example. So you don't necessarily need to get all of these down right now because I will put them into our example so we can go through each step. So these steps are a summary of the theorem on page 444. The theorem says what a maximum or minimum or a saddle point is. These I have arranged in steps to finding those things. So we kind of start off the same way by finding critical points, which we will do in a little bit, by setting the partial derivatives to 0 and solving. So that's the same first step as we normally do for finding maximums and minimums, just we have more than one variable now. The next couple steps are weird, so we'll talk more about these in a minute when we are doing an example. But there are a few key numbers that come from second order partial derivatives. So this is the second derivative test for local extrema. In 2 dimensions, when we had just had XY, we did have a second derivative test for local extrema. It was actually optional to use that because we could just use our increasing and decreasing to figure out if it was a maximum or minimum. We're not going to have that for this chapter for multivariables. Those sign charts really only help us a lot in 2 dimensions. So we have a different way of deciding after we find a critical point, is it a maximum, minimum, or saddle point? And so we're going to have 4 possible cases based on some second order partial derivatives that tell us whether it's a maximum, minimum, or saddle point. And then we will plug in our values to get the z that goes with them. So right now, we're going to talk more about steps 2 and 3 when we get to them in a little bit in our example. But let's start with an example. And I'm going to copy and paste each step so that we can look at them while we're doing the example. So here is our question. So our instructions are to find any local extrema or saddle points of this function. So local extrema are maximums and minimums like we had in chapter 4. Saddle points are not local extrema because they're not a maximum or minimum, they're just a different kind of point. So we are going to find those for this function. And so our first step is to find the critical points. To do that, we need to set each of the partial derivatives with respect to x and respect to y to 0 and solve them. So we would first need to find the partial derivative with respect to x. What is our partial derivative with respect to x here?
2x minus 10.
Yes, exactly. So we look for the terms that have x's in them. That x squared has an x, so the derivative of that is 2x. And this minus 10x also has an x, so that becomes minus 10. Nothing else has an x in it, so those are all considered constants and they all just go away. So that is our partial with respect to x. And so now we need the partial with respect to y. So what will be the partial derivative?
2y minus 2.
2y minus 2. Exactly. So same situation. Those two terms are the only ones with y's in them, so those are the only ones that matter when we're doing the derivative with respect to y. So once we know these two partial derivatives, we can set each of them to 0 and solve. So we have 2x minus 10 equals 0. 2y minus 2 equals 0. So when we solve these, we get x equals 5 and y equals 1. So we just found a critical point. Our critical point is 5, 1. So we know something's going on there, but we don't know what yet. So the next few steps are how we determine whether it's a maximum, a minimum, or a saddle point. So I am going to grab step 2 and copy and paste so we can look at that.
So if this wasn't a critical point and we were looking at like an x and y coordinate, would like the z coordinate be like a circle or something?
So the z would come, and this is whether it's a critical point or not, the z would come from plugging in those x and y into the original function, and we would get a z value. And then those 3 points or those 3 coordinates together would end up being actually a point in the 3-dimensional space.
So it'd be like one edge of the cup or fountain?
It would be, let me come over here. Let's see, yeah, these ones are better. Use their drawings. So like, I feel like the dimensions are kind of weird on these drawings they have here, but like this, like single point on the side of this cup has an XYZ coordinate. So instead of having ordered pairs like we do in XY planes, now we have ordered triples, which is an XYZ. So if we have an X, a Y, and a Z value, then we have just one single point on our graph.
So is it safe to say that Z is kind of like off the graph and away from the graph, making it the third dimension?
So yeah, so if
Does that make
you
sense? Okay.
normally we draw like, lift up my book for a second. We draw like an XY plane on a piece of paper. So you can think of the XY plane is still on that paper and the Z is just coming straight up. So the X and the Y from this coordinate are still the same XY as we normally put on a paper, but the Z is just moving it up in space or down if it were negative.
Okay. Thank you.
So if we have an XYZ point or an XYZ ordered triple, XYZ values, that is still going to be a point. It's just now a point in a three-dimensional space rather than on a flat graph.
So does that mean that Z or like a coordinate could be inside? So like if it was a cup, does that Z coordinate make it to where it can be like a point inside of the cup, like in the middle?
It could be, yeah. So this cup, the difficult thing about drawing things is this cup is infinitely thin. So it's just made up of a bunch of points. So it doesn't have any width, but we could, like if we were able to look inside the cup, we could put points like in there also. But the equation of whatever we're looking at is the equation that relates all of the XYZ points that make up the surface of the cup.
So if we were to like fill the cup, would that be an inequality?
Area.
Yes.
Or
Could you do an
volume?
area of that also? Or volume? Yeah.
We could do a volume, yeah. And everything we know about integrals can expand to multiple dimensions. And we can find volumes of things with integrals. So we can fill the cup with an integral and find the volume that way.
So are every single one of the points that are on the cup an XYZ coordinate and there's no XY coordinates at all?
Correct.
Okay.
Yes. So as soon as we add that, yeah, as soon as we add that third dimension, we can still put like points on this plane down here. Like if we were just looking at this flat plane, we could still put points down there, but all of those still have a Z coordinate of 0. Like if they're not up at all, if they're still just on the flat surface, they still have that Z coordinate of 0.
Okay, that makes sense. Thank you.
You're welcome. Yeah. It's neat. So in a little bit, I'm going to bring up the three-dimensional graphing tool on the internet. So we can kind of look at what these look like there. But I don't want to, but I want to do one example first so we can see how it works by hand and then look at that graph so we can sort of relate what we did to the graph. So back to what we were just talking about, this critical point is just an XY, as we can see. So it looks like a regular ordered pair, but this is just like in chapter 4, we would first find the critical numbers by taking the derivative and setting it to 0, and we would get an X. And so we knew something important is happening at that X. And then we had to do a little bit more work to figure out what's happening with the Y there as well. So here we know something important is happening when X is 5 and Y is 1. But we don't yet know whether that's a maximum, minimum, or saddle point, and we don't yet know the Z coordinate of that. We just know something important is happening in space when X is 5 and Y is 1.
So do we do like a line test for those?
We don't.
Okay.
I think in theory you could. Actually, I don't. I think you could do it like a not very thorough test, but the sort of the word definition of like this being a maximum is that, is that all of the points around it have a lower value. Now I'm thinking a little bit too hard about this, I think. We're not going to make a sign chart because we have the both dimensions and we need to see what's going on for X and Y. And so it would be inefficient to try to do it by like plugging in numbers and see what's going on. We have a better way of doing it.
Okay.
Which is where step 2 is coming in. And this is going to feel weird. So for each critical point AB, which is the 5, 1 we just found, our X and Y, we're going to find these 3 important numbers. A, capital A, is the second order partial derivative with respect to X both times, with our critical point plugged in. B is going to be the second order partial derivative with respect to X and then Y, and C is the second order with respect to Y and then Y. This relates to our concept of concavity in chapter 4. So like a maximum is always going to be concave down. So if our second derivative tells us that we have something that's concave down, we know we have a maximum. Our minimum is always going to be concave up. So if our second derivative tells us it's concave up, we know we have a minimum. That's what we're doing here. It's just a lot more involved because we have more than one dimension. And so these 3 second order partial derivatives together are going to give us an idea of what's going on at this point. So we already know the first order partial derivatives from up here. So with respect to X, it was 2X minus 10, and with respect to Y, it was 2Y minus 2. So I'm just going to write those back down here. So they're ready. So these were our first order partial derivatives. So in order to find A, B, and C, we're going to need the second order with respect to X twice. We're going to need the second order with respect to X and then Y, and the second order with respect to Y both times.
So 2
2, exactly.
for
So we would
xx.
start with that. Yeah, we would start with that 2x minus 10 and then do it with respect to x again, and that would give us 2. If we
And y,
have x,
0.
y, 0 exactly. So we're starting with that same one again, but there's no y's in that at all. So it's really just a constant. So that gives us a 0.
As well as yy.
I wrote
Oh,
y
wait.
wrong. I'm just noticing. I'm sorry about that. This should have been 2y minus 2, not 2x minus 2. Fix that. That didn't make sense. Okay, so if we did it with respect to y correctly, and I write it down right, this is 2y minus 2. So if we're doing the partial with respect to y again, what
It would be 2.
2? Exactly. So this happens a lot. You probably noticed on your homework that a lot of times when we do like the second order partial derivative of polynomials, a lot of stuff just goes away and we end up with something that is a lot simpler than expected. So here we just have 2, 0, 2. Technically, and I want to just do this now because it might happen later, A is this second order with respect to x twice with our critical point plugged in, AB. That is not going to matter in this case because even if we plug in 5, 1, since that was our critical point, there's no x or y in that second order partial derivative, so it's going to be 2 always. But I still should remember that this a, b, and c come from plugging in our critical point to those functions. So our a is that first one with ab plugged in. B is the xy one, which is always 0 no matter what point we're plugging in. And C is with respect to y twice, which is always 2 no matter what we're plugging in. So if we had partial derivatives that still had x's and y's in them, we would have to plug in our 0.51, our critical point, to get our A, B, and C. So that's step 2, is finding this A, B, and C, which uses those second order partial derivatives. So I'm going to bring down step 3 because it is a long step. The work we have to do is not long, it's just a long when it's written out.
Will these steps be given on the test, or will this information be on the final, I should say?
So this stuff will be a part of the take-home final, so it will not be written on the test, but you will be able to use your resources to find it. So we have 4 cases here. All of them depend on what's going on with A, B, and C. And those are the A, B, and C that we found from the second order partial derivatives above. This all this section, this multivariable calculus section, is really like a Calc 3 or even maybe a little bit above topic. So this class is kind of weird in that way because we cover a lot of different, we like span a large portion of calculus in just one term, adding lots of business applications into it. Because of that, we will not be going in depth as to where these 4 cases come from. I will say it has to do with vectors, which you may or may not have seen. Vectors are not a prerequisite for this course, but it's basically when we're looking at the surface. I'm going to go back for just a second. There's a very minimal explanation of this, but if we're looking at around like a maximum, all of the, anywhere we sit around that maximum has a downward slope. Like if you imagine being up there, any direction you walk would be going down. So that is represented in math by a bunch of special kinds of vectors. We use matrices also, which you would have seen before. And that kind of stuff comes from these second order partial derivatives. And that's where all of these inequalities and different cases are coming from. So they're coming from the second order partial derivatives telling us whether if we walk out, we'll be going down or up or to the side. So all of these partial derivatives can tell us that, and that's what step 3 is doing, is comparing our partial derivative with the possible cases. So in this class, we just kind of have to accept that these cases will tell us what's going on at that point. We'll notice that in case 4, the test fails. We won't encounter that in this class, so we don't need to worry about that. It's not that common, so we will always have a case 1, 2, or 3. So let's find our A, B, and C. So we have our A is 2, our B is 0, and our C is 2. I'm just going to write those down here again so they're all ready. So all of the cases want to know what's going on with AC minus B squared. So A is 2.
4 minus 0.
Exactly. So we have
4.
2 times 2 minus 0 squared, which is 4. So that's a positive number.
So does that mean that that is the local maxima?
Not quite. You'll notice that if we're looking at these 2 cases, both case 1 and 2 have AC minus B squared being positive. So we know it's one of those 2, but then we have to look at the next part of those cases. And the next part is, oh, maybe you were just a step ahead of me. The next
Case
question
2.
is
Sorry.
whether A is less than 0 or A is greater than 0. So since A is 2, which is greater than 0, these 2 together fit case 2. So AC minus B squared is positive, which means it's either case 1 or 2. Since A is also positive, we have a local minimum. So there's a local minimum at this 0.51. When x is 5 and y is 1, we have a local minimum. Just like in 2 dimensions, this does not tell us what that local minimum actually is. So we need to do one more step. And that is, I'll bring up step 4. Where is it? Step 4, remember to plug in the xy values into the function to get z. So our actual maximum, minimum in this case, excuse me, our actual minimum is the value of z at this point. So our original function, let me grab it. So this was our original function. So we're talking about a point on this surface, whatever it is. And so in order to get our actual minimum here, we need to plug in our x and y from the critical point to get the z. So our minimum is going to be f of 5, 1. So we have
10.
let's see. Not quite 10. Right, so that's 76. 42.
Is it supposed to be minus 10x, not plus 10x?
Yes, thank you. Okay. I don't know why I'm committed to doing this. So we have does this look right, or did anyone get something else?
I got 10.
Okay.
I plugged it into the calculator, but
Must
I
be
don't know
10.
if
I
plugged
just
it in
noticed I
wrong.
had a wrong plus here too. I don't know why I decided I need to not use a calculator there. Thank you. So we have this local minimum. It is when X and Y are 5 and 1 respectively, and Z will be 10. So that means that what we were talking about before, the 0.5110 is a point on the graph. And so that will be the bottom of some sort of cup or some sort of valley that we see. So that middle step is weird, the one that tells us whether it's a maximum, minimum, or saddle point. But we'll just have to accept that that is a thing in calculus that tells us basically whether we're going up or down when we move from that point. So that told us that if we moved from the 0.51, we would be going up no matter which direction we go, which means that we have a local minimum and it is 10. So I am going to bring up, I posted also in this week's module under today's class, I posted a link to a 3D graphing calculator. For some reason, Desmos has not made a 3D graphing calculator, which is surprising. But this is a different site called GeoGebra, which used to be really popular, but I think Desmos kind of took over. But we can graph three-dimensional stuff in here. It's not always super high resolution, so some things are hard to see, and I think sometimes it doesn't work super well on Zoom, but I'm gonna try it. So one thing I want to note first, these red and green axes are the X and Y axes, and they're not actually labeled right now, but we'll find out what they are in just a minute. And then that green or blue axis going straight up and down is our Z. So this gray surface here would be like the piece of paper that we normally draw X and Y axes on. And then the Z is coming straight up. So this is nice because you can click and sort of drag and move it around as you please. And I put the link up there for your enjoyment. You're not going to be required to graph these things, but I think it's nice to get a visual of what we are looking at here. So I'm going to put, actually, before we put in that, I'm just going to start typing some things. So if we do Z equals X squared to start off with. So if this were a Y equals, I'm going to zoom in a little bit. Now it's hard to see. If this were a Y equals X squared, it would just be a parabola. Now we're doing Z equals X squared. So this is a parabola looking thing. So if I am able to move this so that basically right now the y-axis would be coming straight out from the screen. So the Z is still going straight up and down. This X is going side to side. So now this looks like a parabola if we're just looking at it straight on like a tunnel with an open top. But as soon as we sort of drag it to the side, we can see that it's actually a surface. So this is like if we took a sheet and we're able to morph it into this parabola shape. And if I zoom out, that parabola shape is still there. So these little edges on top are going to keep going out forever, just like a parabola would, but now it's a surface rather than just like a curve on a line. So that's just sort of a random graph. Here's another sort of random graph where we have Z equals X squared plus Y squared. So this is like the cup we were seeing before. So I can drag it and look inside and it just looks like a circle if we're looking straight down into the middle of the cup. But if we look onto the side, we can see it's got this like bottom little shape, and then it's going up in every direction. So maybe from algebra, you remember that the equation of a circle is x squared plus y squared equals the radius squared. So in this case, z would be like our r squared, the radius squared. So as z increases, this circle is getting bigger and bigger. So the circle starts really small on the bottom, and then there's getting like a bigger circle through this cone. So we can get all sorts of crazy shapes here. So I'm going to put in the equation that we were just working with so we can see what that looks like on the graph. There it is. So it's x squared plus y squared minus 10x minus 2y plus 36. And so it just disappeared because I am zoomed in a way that doesn't show it yet. So I'm just going to zoom out, scrolling. There it is. So that is the graph of the function we were just looking at for the problem we did to find the minimum. So our minimum is right down here, and we can see on this blue axis, the z-axis, that's at 10. And so if we were able to look at it straight to the side, that z value, which is the height that it's floating at, is 10, which is good because that's the value we got, or that's the value you got while I made arithmetic errors. But so the bottom of the parabola, or the cup, is 10. And if we're able to look straight down, the axes are not labeled super nicely here, but our x value is about halfway between 0 and 10. So our x value is at 5 and our y value is at 1. So that point at the very bottom of this cup is the point 5, 1, 10. Because it's 5 on the x-axis, it's 1 on the y-axis, and then it's 10 up on the z-axis. I am going to bring up, we're going to do another problem where we're doing an application of this, but I just want to show a saddle point so that we can see what that looks like on here. Let me find it. Okay, so this one is going to be pretty weird looking. This function has 2 critical points. This is actually example 2 from the book on page 445. So we're not going to go through solving it, but we could. But it has 2 critical points. So we can see down here this weird surface. So this is, none of this is filled in. It's all just like a shell surface shape. Down here on the bottom, it's reaching a minimum. So you can see it's kind of got this weird pointy bottom part that's going down there. So that's 1 critical point because it is a minimum down there. And then if I look on this edge, I'm going to go here. We can kind of see a saddle point. So if I look at it to the side, we can see there's sort of this bottom part, but this surface is coming up. And if we move it a little bit over, now the other side is going up. So this is like if you were sitting on a horse, you would be facing one of these directions, either left or right, and your legs would be over on the sides. So feel free to play around with this grapher as you're doing your homework or just plugging in random things and seeing what it looks like. It's pretty fun. I'm going to close it because I think it is making my internet a little slow. It takes a lot of energy for the computer to do that. So let's apply this. So we now we're on these graphs, we're looking at like little peaks and valleys and things like that. But the concept of maximum and minimum applies not necessarily in graphing, but in all of our business application type stuff as well. So this is a profit maximizing problem. So I'm going to leave this up for a little bit so you can read through it before we get started. Okay, so if a ski manufacturer has a yearly profit equation in thousands of dollars of P of XY equals all of that, where X is the number of thousands of pairs of basic model skis and Y is the number in thousands of pairs of race model skis produced each year. So everything is in thousands here. The profit is in thousands of dollars. The X is thousands of pairs of basic skis and the Y is thousands of pairs of race skis. How many pairs of each type of skis should the company produce to maximize profit? So this is a similar kind of problem as we were doing in 2 dimensions, where we had a profit equation and we needed to figure out how many of something they should be producing to maximize profit. Here we're producing 2 things though. So we have to use this method of finding the maximum that we just did in the previous page. So our step 1 is going to be to find critical points. So our critical point in general is where the derivative equals 0. Since we have more than one variable, it's going to be where our partial derivative equals 0. Partial derivatives equal 0. I'm going to copy and paste this down here so you can see it all in one line. There we go. So finding critical points means first finding the partial derivative. So this is a p, so we'll just write p with a little x and p with a little y. So our partial with respect to x, we would go through every term and find the terms that have x's in them, and those are the ones we need to do the derivative of. So negative 66x squared will end up being negative 132x. The second term is 132xy. What's the partial derivative of that with respect to x?
132y.
Exactly, 132y. So the x goes away because there was just one of them, but that y is a constant, so it's staying there.
And plus 132.
Exactly. So that covered our partial with respect to x. So then we would go through and do the same thing for all of the terms with y's in them. Y. So now we have 132x, yes, for that first term with a y in it, minus, so we have 99y squared, so that'll be 198y, minus 66. So we, in order to find critical points, we take the partial derivatives and we just set those equal to 0 and solve. So this one is a little bit more involved solving because both of these equations are going to have both x and y in them. So we're going to take each of those partials and set them to 0. And now this is a system of equations. So we need to solve this. On Thursday, when we're doing our last section of the class, we are going to have systems of equations in just about every problem. This section, we won't really have that many, but I wanted to start reviewing it now so we're ready for systems in 7.4. There are many ways to solve systems of equations. Elimination is one way, sometimes called addition. Substitution is another way. And matrices are another way. I personally am a fan of the elimination method or the addition method, and this system is really good for that. And the reason that I'm saying that is if we look at x, we have negative 132x and positive 132x here. So the point of the elimination method is to add the two equations together to get one of our variables to go away. So if we add these two equations, we get 0 for that first part because negative 132x plus 132x is 0. Then we have our y, which is negative 66y, plus, I'm not going to try to do two things in my head. No. 66. Oh.
Sorry, you were doing so good. I was like, man, she's good.
So adding all of these together, we have gotten rid of that x. So now we have an equation in just y. And this we can solve. So we had two equations, both with two variables. This since x was just a positive 132 in one and a negative 132 in the other, adding these two together just got rid of that x completely, which is the point of the addition, and then we can solve for just y. But then we still need to know x, so we would go back and plug that y into either of our original equations, and we will get our x. So we could do 132x minus 198 times 1 minus 66 equals 0. So negative 198 minus 66. So we have 132x minus 264 equals 0. And adding 264 and dividing by 132 will give us 2. So we are going to be solving systems in section 7.4. So this is hopefully a little jogging your memory a little bit on how to do that. It doesn't come up in this class until now, but it is an algebra thing. So now we have our critical point because we have our x and our y. So that was all step 1. We set those two partial derivatives to 0 and solve. And now we have our critical point 2,1. In general, since this is a word problem, it's asking for us to find the maximum, or to maximize the profit, to find the numbers of pairs of skis we need to make to maximize profit. So it's really unlikely that this is not a maximum. However, we should still go through the steps to make sure, especially since it's important to practice. So we will go on to step 2. Which is to find A, which is, we don't have an F here, we have a P. So A is P XX of AB. So our critical point here is 2, 1. So that's the AB. We need to find B, which is the partial with respect to x then y. Make sure that's right, yes. And C is the partial with respect to y. So we'll have to find each of these second order partial derivatives. So I'm going to bring down those first orders. I'm just going to copy and paste these. Okay. So this is our first order partial derivatives with respect to x and y. So in order to find A, B, and C, we need 3 things. We need P, XX, we need P, XY, and we need P, YY.
For the definitions of A, B, and C, why do we have little a and little b instead of x and y?
Because the A, B, and C come from those partial derivatives with the critical point plugged in. So the little a and little b are representing the critical point. Should make a note of that.
I see.
And that didn't really matter in the previous example because all of our second order partial derivatives were just a number with no variables in them, but we can't assume that it won't happen. So that's a good question. I don't think that was clear earlier. So we first need to find the second order partial derivative without the AB first, and then we can plug it in if necessary. So for Pxx, we already know the partial with respect to x, so we would start with that and then do it again. And in that case, we just have 132. So again, we don't have any numbers in there, all of the, or any variables in there. The second order with respect to x and then y, we would start with that first one again, find the partial with respect to y, and that gives us 132. And then the partial with respect to y twice, we would start with this one.
198.
198, exactly. Negative 198.
Oh, yeah.
So again, in this case, we don't have to worry about plugging in the critical point because there's no x's or y's in any of these second order partials, but I'm still going to write it just for clarity. So A would be this with our critical number 2, 1 plugged in, but no matter what x and y are, we're always going to get negative 132 here. B is the partial of x then y, plugging into 1, but we just get 132. And C is going to be, oops, our partial of y with 2 plugged in. And that's just negative 198. So if we did have x's and y's in those second order partial derivatives, we would have to plug in the 2 and the 1, but we don't. So for step 3, I am going to go back and just copy and paste those cases. And I'm going to put up a poll for you to choose which case applies here. But I'm going to copy and paste them so that they're handy and I don't have to write them. So on your own, look at A, B, and C, which I'm going to write down here again, and determine which case is correct. And I'll put up a poll in just a minute for you to choose which case you found. So the poll is up. So once you decide which case it is, you can choose. So just a little bit longer, 15 more seconds or so. All right, I am closing the poll. Okay, looks great. So we have to remember that when we do this AC minus B squared, we will find that that ends up being a positive number. So this is definitely either case 1 or 2. Just make sure it's easy to like just look up here and see, oh, case 2 has that, so it must be case 2. But both case 1 and 2 have that being positive. So then we have to check A itself, which in this case is negative, which means that this fits case 1. Which is good since we're trying to find the maximum of the profit here. So we should have a maximum. So when X is 2 and Y is 1, we have a maximum. Going back to what the question was actually asking. The question says, how many pairs of each type of skis should the company produce to maximize profit? So the question didn't actually ask for the maximum profit. So we're basically done with this problem. We just have to make sure we're answering the question that was asked. Saying X equals 2 and Y equals 1 is not the answer to this question. So we have to remember what X and Y represent. So we have X is 2, Y is 1.
Z
So
is 0.
Z, we don't know what Z is. We haven't
Oh.
got it. But the question is only asking how many skis, how many pairs of skis of each type we should produce. So X was the number of basic model skis in thousands, and Y was the number of race model skis.
So 2,000, 1,000.
Exactly.
Okay.
So 2,000
Nice.
pairs of basic. 1,000 pairs of race. So that's actually all this question was asking for. It's just how many of each we should produce to maximize profit. Just for fun, I'm going to add a part B, which is what is the maximum profit? So we can practice that last step.
So would X be 2,000 then?
So X is still just 2 because our equation,
Okay.
I'm going to scroll back up for a little bit. All the way back up. So our profit function is saying that this profit is in thousands of dollars. So P is in thousands of dollars and X is number in thousands of pairs, Y is number of thousands of pairs. So X itself is just the 2 still, and Y itself is just the 1. When we interpret that, we would say that means we need to make 2,000 pairs of basic and 1,000 pairs of race, but X and Y are still just the 2 and 1 that we found. So I'm going to copy and paste this again so I don't have to remember it. So our profit function is all of this. So the maximum profit occurs at that critical point we found, 2, 1. So we would go through and plug all of this in. This is long. So we're taking our X and our Y from our critical point at which we discovered there was a maximum. And if we plug that all in, we will get our profit.
I got 80.
Great, that's what I got too.
I was like, oh my gosh.
So this is saying that the maximum of this function is 80. So what would our maximum profit be?
80,000.
Exactly, 80,000. That would be kind of sad if the profit was just 80, but yeah, 80,000.
So when it asks something like, what is the max profit? That's when we do step 4, right?
Yes, exactly. So on the problem like we did before, like if it's not tied to an application and it just says find any local extrema, the extrema is actually the Z value that it reaches, either that maximum or minimum that it actually achieves. And we need to get the X and Y to go with it to do that whole process, but the actual extrema is that maximum or minimum Z value.
Thank you.
A saddle point, I'm pretty sure the book doesn't include the Z value for saddle points in the solutions in the back of the book. However, I think that they should still be found. So it's still relevant. So a saddle point is not an extrema, but it's still an XYZ point on the graph. So let's just check that in our 3D grapher to see what this looks like. I'm just going to put z instead of p of x, y. So I have negative 66x squared plus 132xy minus 99y squared plus 132x minus 66y.
You're in a subscript.
Oh, thank you. How did I get
You're
down
welcome.
there? Oh, no, I can't get out. Okay. No, brother. Okay.
Squared. And then plus 132x minus 66y minus 19.
Thank you.
You're welcome.
Okay, so now that that's actually in there, so this looks weird at first because we can see z is only going up to 4. So this is just a situation of needing to zoom out. But even here, we can kind of look and see this is sort of a cutoff shape. This is an ellipse if we look at it just straight down like this. But if we zoom out, we know that that max was 80 and see if I can zoom to fit. I don't think that's going to work. Yeah, this is maybe why Desmos hasn't made one of these, because it seems to be hard to make it efficient. But as soon as we continue to zoom out, we can see that that little hole on top is getting smaller and smaller. And if we are able to get out all the way to 80, there we see. I know this looks ridiculous with it zoomed out so far on the X and Y also. But that little tiny point right up there is where that maximum is being achieved. So X is 2 and Y is 1, which is why it's so close to that, what we would normally call the origin on the XY plane. But then the Z is going all the way up to 80.
And it looks like you might be able to turn on and off the axis labels. Oh no, just show axis.
Yeah, I know. So if I unclick the show axes, it just takes everything away. So we have this little point. And you can also get rid of the plane. Sometimes I think that gray surface is distracting, so you can take that away as well. And there's a grid as well. So this is fun to play around with to see all of these shapes that we can get. So I want to do a little brief introduction of what we are going to be covering on Thursday, because it's actually related to this. It's another specific kind of maximizing and minimizing. Before that, though, are there any questions about what we've done today?
No, I'm good.
Actually, I'm just realizing there's a little interlude I want to mention. So here we are talking about maximizing profit of just 2 kinds of skis. Most likely a company, at least like a bigger company, is probably not only making 2 things, but all of this applies to any number of dimensions. And if we get into 4th and 5th and 6th dimensions, the visualization kind of breaks down. Our brains are not made for that because we live in a 3-dimensional world as far as we perceive. But the math that we use to find the maximum or the minimum still applies to any number of dimensions. So even if we can't see, like this is a cup with a bottom on it, we can still apply these techniques to maximize and minimize any number of variables. And that's a really big field of math is optimization in all kinds of fields. So if your company is making 100 different types of things, you can make a function with 100 variables, and all of this would still apply. You would be using computers to do it instead of doing it by hand, but it's still the same foundations. And so this is a really fun, awesome thing about math, in my opinion, is that we can take these things that we can like visualize in 3 dimensions and get sort of an understanding of what's going on, and then just take those concepts and apply it to however many variables we need to, and it still all works. Step 3, steps 2 and 3 are a little more involved when we get more and more dimensions, but those calculus 3 concepts that I was referring to would still apply here. We would just have slightly different things to work with. But all of this can be expanded to any number of dimensions we want to, which is awesome.
Okay, so what you're saying is that A, B, and C will always stay the same no matter how many numbers or sets that you have.
Not necessarily, because if we have like, so if we had 3 variables, we would have another partial derivative. Like first order, we would have fx, xz, or excuse me, fx, xy, fx, fy, and fz if we turn z into our 3rd variable and we had some other dimension as our function. Then there would need to be a different combination of these 2nd order partials in order to determine whether it was a maximum or minimum. So
Okay.
this gets a little more involved. This is sort of the streamlined version for 2 variables. But once we add more, we need to start using matrices and things to evaluate these 2nd order partials.
Okay.
So in this class, we won't see anything with more than 3 dimensions, more than these 2 variables, but the same type of thing happens. Math is neat. Okay, since I went off on that little tangent, we don't really have time to start 7.4, so we will save that for Thursday. So you can go a little bit early. Your second to last homework is due tonight, and I will post the very last homework today, which will be due next Tuesday. And please just remember to do that poll to vote for which day the first part of the final is on. And also the student evaluation survey is open through this Friday, so it's really helpful if you can do that as well. So that is all, and I will see you all on Thursday.
Thank you, Madeline. Have a great day.
Welcome, you too.
Thanks. Bye-bye.
Yeah, thank you.